You ever just look around and notice how everything seems to follow these hidden rules? Elegant mathematical rules. Think about it, from the gears in a clock to the orbit of a planet. It's kind of wild. Well, today, we're going to pull back the curtain on one of the most fundamental ones out there. The super simple but really beautiful geometry of what happens when a line just touches a circle. So let's just dive right in with a puzzle. What in the world connects a bicycle wheel rolling on the road and a rope being pulled over a pulley? I mean, they don't seem to have much in common at all, right? But believe it or not, they are both perfect, real-world examples of the exact same geometric principle. The big question is, what is it? To get to the bottom of this, we've got to go back to the absolute basics. Just imagine a totally flat surface, a plane. Now, let's put a circle and a single straight line on it. When you do that, there are really only three things that can possibly happen. First up, the most obvious one. The line can just completely miss the circle. It just sails right on by and they don't share any points at all. Super simple, right? We call this a non-intersecting line. Okay, for our second case, imagine that line gets a little bit bolder. It doesn't miss this time. Nope, it cuts right through the circle, hitting it at two different spots. And yeah, this line has a special name. We call it a secant. Basically, it's a line that slices a circle. And that brings us to our third and honestly, the most interesting case for us today. The line doesn't miss the circle, and it doesn't slice through it. It just touches it. It grazes the circle at one and only one point. This, my friends, is the star of our show, the tangent. But here's the cool part. A tangent isn't just some totally separate idea. It's actually deeply, deeply connected to the secant. There's a kind of magic that happens in that transition from a line that cuts to one that just touches. So just to be crystal clear, a secant is any line that crosses a circle at two separate points. You can practically see those 2 points, right? One where the line goes in and one where it comes out. And this leads to a really fantastic idea. Imagine those 2 points where the secant crosses the circle. What would happen if you started sliding that line, making those 2 points get closer and closer until they're practically on top of each other? Eventually, those 2 points are going to merge into one single point. And in that exact instant, the secant completely transforms. It becomes a tangent, a line that intersects the circle at exactly one spot. And we call that very special spot the point of contact. Okay, so now that we've got a handle on what a tangent actually is, we can start to uncover its secrets. And the first one is a big one. It's a fundamental rule that applies to every single tangent, everywhere. Let's call it the right angle rule. Let's circle back to that bicycle wheel for a second. The ground is our tangent line, touching the wheel at just one point. Now think about a spoke on that wheel that runs from the center hub right down to that point on the ground. That spoke is the radius, right? What does your gut tell you about the angle they make? And if your intuitions scream that they form a perfect corner, you'd be absolutely right. Geometry backs you up. This is our first huge rule. The tangent line is always perpendicular. It forms a perfect 90-degree angle with the radius right at the point where they meet. So how do we know this is true? Well, the proof is it's so elegant. Let's walk through it together. First, just pick any other point on that tangent line, okay? Any point that isn't our special point of contact. Now, since the tangent only touches the circle once, that other point has to be outside the circle, right? Which means its distance to the center is automatically going to be longer than the radius. So think about it. The radius must be the absolute shortest possible line you can draw from the center to that tangent. And what's the golden rule in geometry for the shortest distance from a point to a line? It's always the perpendicular line. Boom! Simple as that. So the big takeaway here is that this isn't just a guideline. It's a non-negotiable rule of geometry. The radius and the tangent will always meet at a perfect 90-degree right angle, every single time. All right, that was revelation number 1. Pretty cool, huh? Now let's see how that builds into our second big idea. This time, we're going to switch up our perspective. Instead of just looking at one tangent, let's ask a new question. How many tangents can you actually draw to a circle from a single point? Well, it turns out it all depends on where that point is. If your point is inside the circle, any line you try to draw is going to slice right through it twice, so you can't draw any tangents. That's a big fat 0. If you're standing right on the circle's edge, you can draw exactly 1. But if your point is outside the circle, something really interesting happens. You can draw exactly two different tangents to that circle. And those two tangents that you can draw from that outside point, they have their own amazing property, which leads us to our second big theorem of the day. The lengths of those two tangents, when you measure from that external point to where they touch the circle, are always equal. Now, how do we know that's for sure? Again, it's just a beautiful piece of logic. If we draw lines from the center, let's call it O, to our external point, P, and then to the 2 points of contact, Q and R, we've just created two right-angled triangles. So let's compare them. OQ and OR have to be equal, because they're both radii. The line OP is shared by both triangles, so of course it's equal to itself. And we know from our first rule, the right angle rule, that the angles at Q and R are both perfect 90-degree angles. So what we have are two triangles that are perfect mirror images of each other. They're congruent. And if those two triangles are completely identical, well then all of their matching sides have to be identical too. This gives us our amazing conclusion. The length of the tangent PQ must be exactly equal to the length of the tangent PR. It's a geometric guarantee. No way around it. Okay, let's hit pause and just recap for a second. In just a few minutes, we've uncovered some seriously powerful and totally reliable rules about how the world works. We've basically just added a few new, shiny tools to our geometric toolkit. So here's what you really need to remember from all this. Number 1, a tangent just grazes a circle at a single point of contact. Number 2, that tangent will always form a perfect 90-degree angle with the radius right at that point. And number 3, if you're standing outside a circle, the two tangents you can draw from where you are will always be the exact same length. And these aren't just some abstract ideas for a math textbook, you know? These are the hidden rules that actually shape the world all around us, from a spinning wheel on the road to the way a gear system is designed. So, with this new knowledge in your back pocket, the final question is, where are you going to spot a tangent next?